now we're again using the same system here. We are going to design a controller for 30% overshoot using A, frequency domain, B, time domain, and well, C is a comparison, so it's not really that important. Now, how do we design a controller for such systems using the frequency domain? Well, the first step is to use, again, minus log overshoot, or basically log E. You can also maybe write it down as ln. Overshoot divided by square root pi squared plus ln overshoot squared. This will give you a specific zeta value, which is in our case 0.356 and 786. So that's the zeta value that you look for. Now, we have a relation where we can find the corresponding phase margin. And this value basically determines the overshoot. And I always thought about the fact that, well, let me just grab the plot. Like this. And if we have minus 180 degrees as the phase value, this point is marginally stable. But if you have marginal stability, what you get is basically you get a sine wave that has peak 2. Therefore, we can think of this as 100% overshoot. So if you have 0 degrees of phase margin, for example, because there is a difference 0, then we have 100% overshoot. If we have a certain distance, for 120, we will, for example, have 60% overshoot. So this difference here relates to overshoot in the frequency domain. And for this, we have two ways. One of them is to use the phase margin relation, zeta and phase margin relation, which is a tan of 2 zeta divided by minus 2 zeta squared plus square root, another square root, 1 plus 4 zeta to the power of 4. So we can use this relation, or to some extent we can use 100 times zeta. So one of them can be used, each of them can be used. Well, it doesn't really matter, because if you use this relation, the angle condition, or the phase margin here, is 39.09 degrees. If we would have used that, it would be 35.786 degrees. So there's not that much difference between them. If you don't really want to bother with that, you can just use 100 times zeta. It depends really. Once we have that, the only thing that we look for is basically the angle condition. So if we have minus 39, then the argument of the system should be minus 180 degrees plus phi m. So therefore, we look for this specific frequency. The angle condition is minus 140 roughly, and the frequency seems to be 0.909. So this frequency is the frequency that we need, and the only thing that is left is to find basically the magnitude here, and that is 0.8037. Therefore, the inverse of that, or k times omega, should be 1 if this is 180 degrees plus something, and therefore this is 1.2443. Now it's interesting because we had k equals 0 as the margin. It's way back to 1.2 to have 30% overshoot. So that's one way of solving this, because it is a very simple and very basic example. Just step by step following the instructions is sufficient in this case. We have a third order system that has an extra pole. Therefore, I'm not really sure what the overshoot is, if it's really 30% or if it's something else. Therefore, we have the time domain part. We'll see the actual model behind this design. And if you get the same gain value, and if you have a dominance factor that is satisfactory, we'll see that this will work. If they're a bit different, then we'll see that there is a better solution. But if you're using the frequency domain, you don't have really that much choice. So let's look at this. Well, we have a characteristic polynomial that will look like s cubed plus 7s squared plus 6s plus 6k. So that would be our characteristic polynomial. And since we know what the zeta value is and we don't know what omega n is, our desired polynomial would be x squared plus 2 times, what is zeta? 0.3578, I guess, omega n, s omega n squared. And we need another pole, s plus p, the reverse pole, since it's a third order system. Now, we have to multiply them. So s cubed plus 7s squared plus 6s plus 6k should be equal to the multiplication of this. And that is basically the following. Well, I've used a, but it doesn't really matter. So s squared times so it's s cubed plus s squared times 0.716, which is 2 times 0.3578. Omega n 716 omega n plus p, and plus s times omega n squared 716 p omega n plus p omega n squared. Of course, I've skipped some steps, but that's not really that important here. You can see that the s cubed terms are basically these. Then we have these equations. So 6s should be equal to this. And the one that's left here is basically 6k, that should be equal to this. So therefore we'll have 7 equals 0.716 omega n plus p. 6 should be equal to omega n squared plus 0.716 p omega n. And of course, 6k should be equal to p omega n squared. Now we have omega n, p, and k, 3 unknowns, 3 equations, but these equations are a little bit painful. And the basic fact about that is, since we have only overshoot, we only know this part here. And our desired polynomial has a squared term here. And if you multiply them, you'll get omega n squared times p, which is highly nonlinear. In this case, we have also this multiplication here, which doesn't happen if you know what omega n is. Because if you know omega n and you don't know zeta, this is basically linear. And linear times linear is not really that big of a deal. But in this case, it's a bit harder. But we have to solve this. Of course, it would be wise to use the first 2 equations here to eliminate p or omega n as your choice. I guess p is better to eliminate because you know what p is here, you know what p is here. But you have omega n squared, so therefore you should basically do the following step. P should be equal to 7 minus 0.716 omega n. Plug it into this, so 6 equals omega n squared plus 0.716. And then 7 minus 0.716 omega n times omega n. Hope that I'm not wrong. I guess. So then you have 0.716 squared omega n squared, you take that out. 1 minus 0.716 squared should be omega m squared, and then we'll have basically minus 0.716 times 7 omega m times should be. So it's again a second order polynomial. We have to solve that in order to get omega values. And yeah, the omega value is solved as 1.083 and 3. So that's omega. If you know omega, you can work out what P is. So let me write that down. P is equal to, and it is important what the value of P is. And P is equal to 6.22 roughly. And the K value here seems to be 1.2176. So this is the solution of the system. Now we have omega equals 1.08, zeta is equal to this, so it's roughly 0.4. So 0.4 and 6, so 6 divided by 0.8 is 2 times zeta omega, or 0.4, is a good ratio to have if you are looking for accuracy for the system, because 30% overshoot you have to have a dominance factor. Since you have a third order system, you have only a relation for the desired one, but it seems to us that it has a good ratio here. So 10 times 12 times is basically satisfied. Even 5 times works well, so therefore we should get the overshoot value that we look at. And you'll see in the PDF that this really works. You can see now that here, this here is basically very standard. You have an algorithm here, look for zeta, look for the phi m value, add it to minus 180 degrees, look it up for the angle condition from the phase graph, come up with frequency, look for the gain value, take the inverse, and you're done. Here we have more modeling involved. You have to look for a desired polynomial. If your system is a higher order system, you have to add a residue pole to it. And then you have this algebraic method, just calculate everything, it takes more time. But you can evaluate your solution and see that if it's really working, if it's a good one or not. By the way, there is a slight difference. You can see that it is 24, whereas we have 21.7, so it's not really that big of a deal for such a system because they're close enough. But yeah, we see that, and this should give us the overshoot value. But the frequency method does not really use or utilize the system transfer function, but the time domain does. So there's a huge difference in that manner. But we can see that they give basically approximately the same result using the design. So that's basically question 2. Now, question 3. Using the previously defined p-type controller, design a leg controller. So we are going to design a leg controller that basically halves the velocity error. Let's say the question, you have a p-type controller. We have already designed the controller. So add a leg part to it so that we have velocity error half. So this means basically the following. If we have a certain difference in the ramp response, we want to increase the performance of that so that it's basically looking like this. So if this is a certain distance, this is 2 times the difference. So that's what it's basically all about. If we have position error, then we are looking at the step response. If we have velocity error, we are looking at the ramp response, etc., etc. So, well, in order to evaluate what's really going on or what should really happen, we have to look for the velocity coefficient, which is basically defined in order to examine the velocity error itself. This inverse will give us the velocity error here. And we can do this by using this limit. So limit s goes to 0, s times k times gs. So we have a certain k value, and we know what gs is, so basically we can plug that in. So this limit is basically s times, and what is my k value that I've used? 1.24 times 6 divided by s cubed plus 7s squared plus 6s. So I've plugged in the system, the previously designed p-type controller, and I have an s term. So immediately you can see that they cancel each other out. This limit becomes 1.24 times 6 divided by s squared plus 7s plus 6. And this is basically 124 times 6 divided by 6. 1.24, or the p-type controller itself, basically. And the velocity error here becomes 1 divided by kb. Therefore, this is 1 divided by 24, or the p-type controller. That gives us 0.80366, etc. So, what we want to really do is we want to add a lag controller in order to come up with a new one, let's call it EV new, that should be equal to 0.4. So half that, so 0.40183, something like this. So we want to increase the gain by 2 because this is basically half the error. So in order to do that, I can just see that this would be same as 2 times 1 to 4. That's basically it. So this should be the gain that I add to the system. So instead of having s times 1.24, I want to have times 2 times 6 divided by s cubed plus 7s squared plus 6s. If I calculate this limit, then I see that I get 0.4 as the velocity error. Therefore, I can combine the controllers or I can leave them separate, so it's really up to you. Let's add tau s plus 1, alpha tau s plus 1. So this is the lag part. And then I have a certain gain. In this case, it is 2 times 1.24. And then we have the system. So this is basically the whole controller part. So instead of this, maybe we can use 2.48 roughly. So we want to add the lag controller so that we have again the same overshoot, so 30% overshoot. That shouldn't change. Now we will use the frequency domain method for once, and we'll also talk about the time domain and then see how they relate to each other. So for the frequency domain method, what we have to do is we have to basically convert this into the following. Let me just use this part here. So the lag part times 6 times 2.48 divided by s cubed plus 7s squared plus 6s. So we are basically looking at this scenario. So this is our closed loop system, and this is our loop transfer function here. So we need the body of this for the frequency domain. Not the original system, but this. We can use the original system because, well, the only thing that changes here is the gain. So we can just multiply that with 2.48, and the angle condition is the same. So it doesn't really affect the body graph that much, but it's up to you. If you're in an exam and you don't really have the body plot corresponding to the system, then you have to work your way out on your own. Well, yeah, remember that we want to have overshoot 30%. Therefore, we had a phi m of 39.0, what is it, 9 degrees. So these are still there, but if you remember, we have the argument of tau s plus 1 divided by alpha tau s plus 1 times gs basically. And this will have a certain effect to the phase angle, but we want to have basically minus 180 degrees plus phi m. Even though we have designed a lag controller. So therefore, if this is, for example, minus 10, then you'll see that it becomes plus 10. So if we are searching for the phase graph, we'll search for plus 10. Because if this will contribute negative 10, since it's lag controller, we'll get the same phase angle there. So we are trying to be safe a little bit, or to compensate the value that will be added from lag controller. But the basic assumption here is that it should be less than or equal to 10 degrees. So that's really important. Because the lag controller does not try to update the transients or change the behavior. It tries to update the steady state behavior, as in this case, and not affect the transients of the system. So that's why we have to add 10 degrees. So once we've done that, we're basically searching for, let me see, did I write it down? We're looking for minus 128.909 on the phase graph. And the frequency for this seems to be 0.644 radians per second. So we need to find out what the frequency is, or where on the frequency scale this is satisfied. Once we have that, our alpha is basically the gain. At that point, 0.644. Now I write this like T, but it's basically the whole gain here at that frequency. So if you use an updated body plot, you can just use this. If you're using the actual body plot of the system, then you have to have 2.48. So it depends on your body graph. If you have the raw system body graph, this is the relation that you should use. If not, if you are using the updated one, then it's already included in the gain. So let's assume that we are using the updated body plot. You plug in this and find out that the alpha value for your lag controller should be 3.229. That's one part. And for roughly omega star tau equals 10, we have tau equals 10 divided by 0.4644, which is basically 15.5. Therefore, your lag controller should be 2.48 times 15.5 s plus 1 divided by alpha times tau, which gives us 50.5246 s plus 1. So this is the frequency domain design. You can see that, again, it is pretty much algorithmic. You have a plan, you just look for the actual gain, the loop transfer function gain. If you have chosen that gain, then you just add it to the system or to the body graph. And once you have done that, you just look for phi m, but since you will have a contribution from a lag controller, you're just adding 10 degrees or assuming that it will be minus 10 degrees or less than that. So, yeah, what you can do is basically you can check out what the actual angle contribution is. But if you're in an exam, you shouldn't really do that because it's not really important. It is important that you can design a lag controller, you can decide on the values, and well, since you don't really have a computer for that, you cannot really verify or validate your results. So yeah. this is sufficient there, therefore you don't really have to iterate through it. So this is the frequency domain solution. So let me just go ahead and get rid of this part and look for the time domain solution. So, for the time domain, the thing that does not change is the gain value. 2 times, what was it again? 1.2443. So, this is basically the gain that we should get. But if we define the lag controller, we pretty much define it like this, S plus P. So therefore I'm going to leave out this 2. I have that in my mind, I'm just holding on to it. I know that the previously designed p-type controller is this value here. And if I look for the limit s goes to 0, fs, it will basically show me that the end result looks like this. So the gain of the controller is actually kp, the p-type controller, times c divided by p. And now I want to have the effect that this is equal to 2 times kp, because of the howling here. So therefore, I can see that the z to p ratio should be equal to 2. Now, note that we are using alpha and tau. So here, if you plug in s equals 0, you have gain 1. So the DC gain of this whole thing is equal to 1. Therefore, you will have 2.48. So that doesn't really change. Here, we want to affect with the position or the location of the 0 and the pole, such that we have the corresponding 2.48 value. Therefore, I'm leaving that to the ZP ratio here. And that's basically it here. We have the only information that Z to P should be equal to 2. Now, let's have the root locus here. What was again is cube. Let me just write that down. 7x squared plus 6s. So one at the origin, I guess minus 1 and minus 6. Yeah, it seems all right. And we have a certain zeta value. Let's say that this is 30. So this is the zeta equals, what was it? Do I have it somewhere? 0.35, as far as I remember. So I don't really know what the frequency is, as it was the case in the p-type controller. But this is basically the body plot that we had. And it seems like we have chosen this point here. Because it's on the root locus, there is a certain OEM value, etc., etc. Now we want to increase the gain so that we have 2 times that, and let's assume that it corresponds to this position here, because k increases. Therefore, somewhere here is our actual solution. But can you see the problem here? If I increase the gain k 2 times, instead of picking in 1.24, I'm just picking 2.48. Then I will have a lower zeta value. This will be higher overshoot, and I don't want that. But if I do this, my velocity error will be increased. The performance of the ramp response will be better. So I still want to do that, but I don't want to have high overshoot. So I have to design a lag controller, which has a Z-P ratio of 2. But now the problem is the following. Here, in terms of root locus, we have some angle contributions, and some of the angles are fixed to a certain value. And then we have the gain condition. There's also the gain condition that gives me exactly this point. And, well, if I'm adding poles and zeros, which I'm doing here, I'm adding just one pole and another 0. I don't really want to change, basically, the overall angle condition on the root locus. Because if I do that, my whole behavior will change because it will not correspond to this point anymore. So it should have roughly the same sum in terms of the angles. So what is the best point to introduce a pole at 0? That's basically the question in timeline. And therefore, something that relates to this here is 10 degrees. The difference shouldn't be greater than 10 degrees. So if I'm adding a pole and a 0, it shouldn't really change that much. Now, let's, for an example, introduce it somewhere here. So since it's a lag controller, we'll have a 0 and a pole. Now, if you look at this, you will see that the difference here will not be that much. But the problem here is, of course, it's on the right half plane, so it's not really that what we want to have. And, well, if it's here, let's have it here, the angle contribution might not be, again, that relevant, but since it's far away, it doesn't really have that effect. So it's not really affecting the system because it's out of the dominant region. So if you want to design a lag controller, we still want to have this angle condition here. So they should not contribute more than minus 10 degrees. So therefore, instead of choosing it on the right half plane, of course, and here it doesn't really work that much. But since we don't want to have that big of a difference in angle, we want them to stick together. So therefore, we can introduce, for example, the pole here somewhere, and the 0 here, and hope that the difference from here to here is not that big. So in order to ensure that, I'm going to push them towards the origin as far as I can. But it's dangerous because we will have another pole here. We have already one at the origin, so I should be a little bit careful. And therefore, for example, I can choose the 0. We have zeta omega n here. I can choose it 10th of the dominant value here. So this is zeta times omega n. And dividing that by 10, by 20, by 50, I can choose 1, 0. And then I can calculate where the pole should be because I have a 0 to pole ratio of 2. So they are not really that independent, but I have to choose one of them. This equation on its own shows that there are infinitely amount of solutions to this problem, so you can choose whatever you want. The only limitation is that the angle contribution should not be that big, and the ratio should be equal to 2. And that's it. And if the overall closed loop system is, of course, stable, you're good to go. So therefore, I'm going to make a random choice here, and let's say zeta omega n is the dominant part, the real part of the dominant poles, and divided by 10, so 10th, so it should be close to the origin. If I do this, minus 0.1 times 0.35 times 0.909. So this is basically it, and it seems to be equal to, of course, the negative sign is there. So it's negative for the 0 value itself, the positive, of course, is 0.035. Pretty much at the origin, but not close. But not exactly, it's just close. Therefore, if I have the 0 value here, phi is equal to that divided by 2. So the half of that is basically p, which is 0.0175. So I can choose this pair, but it doesn't really have to be like this. You can just have 0.01, 0.1 even, they all work. Then just half of that should be p, and you're good to go. So one of the controllers that I can choose here is basically, it has 1.24 gain, s plus 0.035, divided by s plus 0.0175. So that's basically it. Now, if I convert it into, well, I didn't convert it, but you can look up where the zeros and poles are and see if they're really close or not. But they don't really have to be the same, because we are choosing it based on the ratio here and a certain angle condition. Therefore, they might not match, but their response should be close to each other. So yeah. It seems like on the right we have a better way of choosing it, because we definitely find out what alpha should be, what tau should be. We just directly calculate that. But here on the left-hand side, if we have time domain approach, we have to basically choose it based on the ratio. What you can do is, of course, you can go ahead and use maybe tabulation or stuff like that to look up the velocity error, which one is the best. If it's the best, let's choose it. But since we're thinking in the classical exam manner, we just choose it based on the ratio here. So that's basically question 3. Okay, now we have designed a lag controller in Q3. Now in Q4, we're looking for a lead controller design. And again, we have the same overshoot value, 30%. And that's basically it. The only difference from the previous system is that we have a 0 S+2. So in order to be able to design a lead controller. So we are again going to use the frequency domain, and then we'll talk about the time domain. So yeah, let's start with the frequency domain. So again, zeta 3, 5, something. It's not really that important at this point. And then we have phi m. What was it? 39.09 degrees. So these are still there. So what do we have here? So the we look for the system's phase margin before we start anything, and for the phase margin, we have basically this condition, because we look for the argument of g omega, and basically the difference of 180 plus phi m gives us the phase margin of the system, of the actual system. So I'm going to stick m here, because we have phi m already. This is the desired phi m, but the system has a different phi value. We are going to design a controller that fixes that. So yeah, if we look up the gain condition, I'm not going to use the symbolic equations here because it will take too long. But I assume that we have a body graph, so I'm going to look for 0 decibels, or if it's gain just equal to 1. And at that point, I'm looking at the frequency. So at what frequency is the system's gain equal to 1? So that's basically the question. Then I'm going to look for the argument, and then the difference from 180 degrees. That's going to be the phase margin of the system. Now, this happens at exactly, what is it? 1.38 radians per second. And if I plug that into the argument here, I'll see that this is minus 122.48. So I'm going to solve this as the phi value, and this phi value is equal to 57.51. Yeah. Now that's it. Then we have something called phi max. As it was the case for the lag controller, where we had the argument tau s plus 1, alpha tau s plus 1, and we've assumed that this will be less than or equal to minus 10, we have the assumption that the dynamic part will have phi max at as its maximum value. So we are going to look up that value, or calculate that. So phi max will be the phase margin that we look for, this value here, minus the system's phase value, plus 10 degrees. Again, we have a thing for adding 10 degrees to stop. So yeah. So this value is 39.09. This value is 57.51. And then we have plus 10 degrees, which gives us phi max of minus 8.42 degrees. Now, from this point on, we can just calculate what beta should be, since alpha is for lag, beta is for lead. And this is minus sine of phi max, 1 plus sine of phi max. So these relations are basically in the textbooks. If you're curious how and why do we use these steps in order to design a lag controller or a lead controller, you have to look up to the control textbooks, because one of them was really explained well. But yeah, at this point it is really important that if you're using a calculator, you have to be careful here. Since if this is degrees, you have to use basically the degrees version of sine. If you're in radians, you have to convert it into radians. So therefore this is really important. Since I have used method, I guess I've used just minus 0.147 radians. So, and I've plugged in that into the sine. So if you are using sine degrees, so just plug it in here. If not, convert it into radians, then use that. So based on this relation, we find out that beta should be 1, 3, 4, 3, 2. So these are basically the steps that we should carry on. And then we have M max, which is the magnitude, the maximum magnitude, which is 1 by pi squared of b. Since we know what b is, big beta is the square root of beta and its inverse, can calculate it directly in 86. And yeah, now up to this point, we have done the following. We have looked at the system's phase margin, the phase margin that is desired, shows the maximum phase value accordingly with 10 degrees increment. And then we've used that phi max in order to come up with a beta value, which is one of the controller parameters. Then we get a maximum magnitude. Now this magnitude is important because we are going to search this magnitude. So we're looking for the frequency where we have approximately this. So this point needs to be searched. And at what frequency value can we do that or get that? That's 1.245. And instead of looking up a certain phase value degree or a certain gain, we're looking for 1 by m max for this controller. Now, if we have omega, then we are basically done because our last parameter is 1 by omega squared of beta. Now, it doesn't seem to be making any sense because we are basically skipping steps here. But these calculations are derived in textbooks, as I thought. So you should just be aware of how to use it or what corresponds to what. And if you're curious, you can check it out. So the tau value here becomes 0.69267. That's basically it. Then the lead controller is beta tau s plus 1 divided by tau s plus 1. And basically we get 0.9304 s plus 1, 0.692 s plus 1. Or 1.34 32 s plus 107 5 s plus 114 4. So you can see that this value pops up here, which I've seen somewhere. Mx should be that, the inverse of Mx, I guess. No, it is the beta value. Yeah, that's the beta value. Because tau is cancel out, it's the beta value. So, yeah, it's not really that interesting to design a lead controller if you are kind of trying to teach it in a classroom, because it's too algorithmic, even more algorithmic than the lag controller. You have to find the phi max value, transition into beta, use the beta value to come up with a gain value, and then look up that inverse of the gain value. You have tau, and then we're basically done. Now, for the time domain solution, it's basically left to you as an exercise, but what we really do is we just use k s plus z divided by s plus b. You can maybe omit the k part because we already have z divided by p as gain value. So we have to add this to the system. So s plus 2, and then we have 6, and then there will be another s squared plus 7, s plus 6. It's basically the loop transfer function. Then you will use the algebraic methods. So the closed loop is a 4-quarter one, 4-quarter PCS. So therefore, we have only, again, the overshoot value here. So omega n is an unknown. So a and b, assuming that your residual polynomial looks like s squared plus as plus b. We don't know what a and b is, we don't know what omega n is, we don't know what z and p should be. But since it's a 4-quarter equation, we have 4 equations. So omega n, a, b, z, p makes us 5, I guess. 5 unknowns. So therefore, four equations. Therefore, we have to parameterize that. Maybe choose z, maybe choose p, and then try to design one. If I'm going to design one, and if it's not really required to be optimal, I might go ahead and choose omega n in order to come up for just a working solution. But again, a and b should be basically positive values in order to have stability, etc., etc. So this part is basically a bit harder to do in the time domain because there's an optimization problem waiting on for us. So yeah. But since we've talked about too much in the semester, I'm not going to go into too much detail and bore you with all the equations and all the solutions because it doesn't really make sense. It's just numerical stuff. So yeah, if you are going to design a lead controller, you have to just write down the steps and carry it on. It's not really that complicated and also maybe not that exciting. So that was Q4. So now we have a 1 second delay. We've added a second delay to the system. And we will be looking at, again, the P-type controller for the system with delay. Well, first we look for the zero delay for no e to the power of minus s and to be with e to the power of minus s. And then we will compare that, basically. So, now, let me see. Okay. So actually we've worked out what the stability interval of the system without delay is. Namely, it was gs 6 divided by s cubed plus 7s squared plus 6s, and it was between 7 and 0. So that's the first part. Not really that exciting yet. Now, what about adding a certain delay value? Now, Again, if we have the body plot, of the whole system, 6e minus s divided by s cubed plus 7s squared plus 6s. If we have the body plot of this, it's not really that big of a deal, because we will look for, again, the argument should be minus 180 degrees. At that frequency, we will get 1 divided by g omega. And that will be it. But what if we don't really have this late part, but we have the body of 6s cubed plus 7s squared plus 6s? What then? Can we use this body plot in order to come up with a controller for the actual system that has the lake? Well, obviously we can, because we have k times gs times e to the power of minus s. And we're basically looking for 1 and minus 180 degrees. And as we thought previously, the magnitude of this, if that should be equal to 1, this has really no effect. Therefore, we can just use equals 1, take the inverse, and use the same value. So this also means that if we have a certain body plot, let's have a body plot here. Let's assume that this is the body plot. And maybe something that important. It means that if we add the lake to the system, we will again have the same, I didn't plot it very well, but sketch it very well, but we will have the same gain, because it doesn't really affect the gain value here. That's not relevant, it's not really important. You will have the same gain. But the problem is with the argument here, the phase condition, because the argument of k times g times e to the power of minus 2s should be equal to negative 180 degrees. The problem with that is that argument k, if k is positive, is 0, so argument of g omega plus argument of e to the power of minus j omega should be equal to 180 degrees. And as I've already talked today about this, this is minus omega. But the problem here is that this is in radians, but this is in degrees, so times 180 divided by pi. You have to take into account this part here, because that will be subtracted from the system. Now, let me remind you that this frequency is logarithmic, and you have 10 to the power of minus 1, 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, etc., etc. Now, plug in 10 to the power of 2. So, this part here, let's take it roughly 3. This is 60 degrees. 60 times 10 to the power of 2. Something like this. Minus 6,000 degrees. Incredible, because it's such a high value that, well, basically we have an interesting plot. But we can see that if you are plotting the body plot of the system with the lake, it directly tends to minus infinity, because we're subtracting a huge amount of phase angle. And if omega tends to infinity, this tends to infinity. Therefore, we have to basically take into account that we have such a difference here. But it's not really that easy to calculate this, because, well, this depends on omega, this also depends on omega, and I'm not really finding the exact value here. I cannot really find the value here. So what I can do at best is to approximate or guess what omega looks like. For example, I know that this is between 0 and 7 without the delay. So if it's somewhere here, for example, if this is the line, the frequency that was for the non-minimum phase, for the minimum phase part, then I know that a previous frequency should be my concern because it goes down. So it will hit minus 180 degrees before the minimum phase part hits minus 180 degrees. So yeah, you can start with a guess. For example, if you guess that omega is equal to 1, just roughly guessing, then we should look up what the argument of this is. So argument of j omega here minus, let's say 60 degrees, should be minus 180 degrees. So if this is roughly 120 degrees, then I'm at the correct point because it satisfies the equation. If it's low, I might have to increase omega because it still didn't hit 180 degrees. So I have to kind of play a guessing game here, and I have no other choice because it's highly nonlinear. The only thing that I can do is basically guess. Because if you want to take into account the whole thing here, you will have, again, a tan of, what was it again? Minus omega cubed plus 6 omega divided by minus 7 omega squared plus, or minus in this case, omega times 180 degrees divided by pi should be 180 degrees. So this is maybe the exact equation, but we have a tan on the left-hand side, we are subtracting some value from it, and it should be equal to minus 180 degrees. The best we can do is just try certain omega values, a lower omega value, a higher omega value, and maybe just take the mean and try to find the point where this really happens. So, or if I use, for example, MATLAB, I can find out that the frequency here is 0.779. So if I would start with 1, and the reason behind that is I'm just looking for the multiplication. So 60 omega, and then also the argument at that omega. So I'm trying to use this here. So omega should not be really huge. Omega cannot exceed 3 here because it will be minus 180 degrees on its own. But the system itself has also a certain phase value. Therefore, I have to track that and combine these two informations in order to approximate what omega is. If you hit a point that is almost the solution, you can just iterate or just use linear iteration. One a bit lower, a bit higher, and then the exact one. This is called actually extrapolation, but you don't really have to go into detail. So, at exactly this value here, I see that this and this brings up minus 180 degrees. So then I can just look up what the gain value is and use that gain value in order to come up with the gain value. So it seems to be equal to 1.10038, which is 0.9964. So, yeah, if you remember, we had a design where we talked, it was the first question, I guess. We assumed that we can only have gain 1, and how much delay can we add to the system until it's marginally stable. The value of the delay was 0.99, but the gain value was equal to 1. So you can see that we have approximately that case here. So it's a special case that is chosen here. So I have basically added 1 second of delay instead of 0.99, and then we see that the gain value should be 1.0038. So it's basically compatible with question 1 because it's basically the same system. And yeah, what can we say about this system? Well, instead of having a stability interval for 0k7, now our stability interval is roughly 0.99. So you can see that this negative argument effect, this one here, changes and reduces the stability interval. If a system has delay, if you add delay to the system, the stability decreases. Because we are safe if we are far away from 180 degrees. So the phase margin here, plus phi amp. If phi amp is high for a system, then you can compensate more and more delay. Because you're far away from 180 degrees. If the phase margin is low, if you don't have that huge phase margin, then you're basically in trouble. Because you're close to the j omega axis. So you're close to this whole j omega axis. If this distance is not that big, if you don't have a phase margin that's large enough, that's the stability measure actually. Of course, you have also the gain margin, which is the p-type controller itself. The higher the gain margin, the better it is. You can add more and more gain to the system until it's destabilizing. So yeah, that's basically it. And for this system, we can see that adding delay decreases the stability interval. If you, for example, add 0.5 seconds to it, you will have a greater k value there. It's just obvious based on the fact that you will use this relation here. And this will not be 60, it will be 30. So you will hit later this 180 degrees margin. And therefore, your gain will decrease and your k will increase. So that's basically question 5.